In this video, we are going to show that X bar is an unbiased estimator for mu. Let's jump in and see exactly how that works. So the key here is let's check out how it's unbiased. So we need to start off with that definition. What we'd really like to do is show that the expected value of X bar equals exactly mu. So how are we going to do that? Well, we are going to say, all right, well, let's look at X bar. Our expected value of X bar is really equal to the expected value of the sum of xi from I equals 1 to n divided by n, right? That's all X bar is the sum of all the x's divided by how many ever x's you added up. All right, awesome. So at that point, we can say, well, we have this special property of expected values that I can just pull that in right outside. So that's really the same as 1 over n times the expected value of the sum of xi, I equals 1 to n. Okay, that's nice. And so I can have another property of expected values that I can bring it inside the sum. The expected value of a sum is the sum of the expected values. So if we do this and we say equals 1 over n times the sum of the expected value of xi, I equals 1 to how many ever my sample size is. Great, and that equals 1 over n times, if we just kind of wrote it out here, we'd say that is expected value of the first one, x1, plus the expected value of the second one, that's x2, and you keep doing that till you hit the expected value of the last one, xn. Great. Okay, so we'll close that off, boop, just like that. And now we'll note that this is equal to 1 over n times, well, what's the expected value of xi? It's just mu plus the expected value of xi, oh, that's mu, plus dot, 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 dot. What's the expected value of xn? The expected value of x, no matter what x is, xi, x1, x2, all the way to xn, they're each mu. So that is mu, that's 1 over n times mu plus mu plus mu, all n times. And so that equals 1 over n times, and then this right here is mu plus mu plus mu, n times. Well, that's n times mu. So 1 over n times mu is equal to mu. And so at the end of the day, we have the expected value of X bar equals mu. So I'll just write it in here. We've got the expected value of X bar as a conclusion equals mu. And thus, X bar is an unbiased estimator for mu. We're going to use this idea, this concept of unbiasedness later on in the chapter. So good job. That's what unbiased is. That's the definition of an unbiased estimator, and that is showing that X bar is an unbiased estimator of mu. See you in the next one. Okay, let's show that sigma hat squared is an unbiased estimator of sigma squared. So in order to do that, what we're going to have to do is first have some identities. So let's check those out. The variance of x is equal to the expected value of x squared minus the expected value of x squared. And we'll recall that the variance of x bar is equal to sigma squared divided by n. And sigma hat squared is defined to be the sum of xi minus x bar squared divided by n minus 1. That, of course, is a function of the data, and that's why that is an estimator. So to show that sigma hat squared is an unbiased estimator of sigma squared, we're going to have to show that the expected value of sigma hat squared is equal to sigma squared. Okay, we're going to need lots of room, so let's get started right about here. And we'll say, all right, if we want to show that, we're going to start with the expected value of sigma hat squared is equal to, from here, the expected value of the sum of xi minus x bar squared divided by n minus 1. And we're off to the races. So this will be equal to, that's a constant, so that's 1 over n minus 1 times the expected value of the sum of xi minus x bar squared, and then that is equal to 1 over n minus 1 times the expected value of, now we're going to map this out, so that'll of course be the sum, that's of I equals 1 to n, I equals 1 to n, of, that will be xi squared, and if you FOIL that out, that'll be minus 2 xi x bar, and then that will be plus x bar squared, and that's all the big sum there. And we'll close that off. So this will equal 1 over n minus 1 times the expected value of, and we'll make this the sum, it'll just be understood to be I equals 1 to n of xi squared, minus 2 is a constant, and x bar will come out, so it'll be minus 2 x bar, because x bar is just a number, the sum of xi plus the sum of x bar squared. Great. And thus that will be, we'll close that off. Okay. So what we're going to do is I'm going to make another little identity over here, and note that that's the sum of xi. We know that x bar equals the sum of xi over n. Thus, that means that the sum of xi equals n x bar, and that's going to be very convenient for us, because I'm going to rewrite this. We want to conserve our real estate here. We're going to need all of this. This is the expected value of the sum of xi squared minus 2 x bar. That's the sum of xi. That's the sum of xi. So that's n x bar plus, and that's the sum of a bunch of x bar squareds. So that's just n x bar squared. We're going to simplify as much as we can before we bring that expected value in. So that'll be 1 over n minus 1 times the expected value. We'll do one more step of this. It's the sum of xi squared, again from I equals 1 to n. Now this is n x bar, and that's 2 x bars. So I'm going to skip a step here, right? This is minus 2 n x bar squared, right? X bar squared, or x bar, and x bar is x bar squared. So that's minus 2 n x bar squared, and that's plus 1 n x bar squared. This is going to leave us with minus, right? That's going to leave us with minus n x bar squared. There's 2 n x bar squareds here. There's 1 n x bar squared here. So that's going to leave us with minus n x bar squared. Okay. So this equals 1 over n minus 1. So we'll bring that expected value in now. We know that that's equal to, good, the sum of the expected value of xi squared minus the expected value, that n will come outside, of x bar squared. Okay, so now we're going to use our identities finally here. So I'm going to use this one and write something down here. If that is true, then we can remake that as the expected value of x squared, whatever that is, whatever that x is representing is equal to, and then I'll just take this piece over there. So that's equal to the variance of x plus the expected value of x squared. Great. So we've got that. And so I'm going to use that right here. So that's going to equal 1 over n minus 1 times the sum of the expected value of xi squared. So the expected value of xi squared is this, right? For each xi, for each xi squared, for x1 squared, x2 squared, x3 squared, the expected value of that is going to equal the variance. And so what I'll do here is we'll call this the expected value of x squared equals sigma squared plus mu squared. Because the expected value of x is mu, so that's mu squared. The variance of x is known to be defined to be sigma squared, and so we've got that. So this is going to be this n times. So that is, because that's the sum of constants, right? Sigma squared is a constant, and mu squared is a constant. So that'll be n times sigma squared plus mu squared. Great. Now, what about this one? This is minus n times, but what is the expected value of x squared? I'm sorry, the expected value of x bar squared. So we can do the same game here. The expected value of x bar squared, it's just whatever's being squared in there, is equal to the variance of x bar plus the expected value of x bar squared. Awesome. Well, that's equal to sigma squared over n, that's the variance of x bar, is sigma squared over n, plus the expected value of x bar, we've established is mu, so that's mu squared. Awesome. So the expected value of x bar squared is simply sigma squared over n plus mu squared. All that times n. Okay, great. We got to make the most of this room we got down here, but it's just a little bit of algebra left. 1 over n minus 1 times the sum of n sigma squared plus n mu squared minus sigma squared, because n and n cancel, minus n mu squared, n times mu squared. And what does that leave us with? Equals 1 over n minus 1 times the sum of, so there's plus n mu squared, there's minus n mu squared, so it's just going to be n sigma squared minus sigma squared. I've run out of room down here, so I'm going to go this way. Equals, so that's going to be 1 over n minus 1. I'm going to factor that out. So that is, right, I'm going to factor out a sigma squared, so it's sigma squared. And that'll leave us with an n minus 1. And aha! I've got 1 over n minus 1 times sigma squared times n minus 1. That n minus 1 and that n minus 1 cancel, and I'm left with sigma squared. Aha! So at the end of the day, I have the expected value of sigma hat squared equals sigma squared, which means sigma hat squared is unbiased estimator of sigma squared. Nice job. Quick note, right? It helps to just write this stuff out, not to just watch it, but to get out there and write it out. Get a sheet of paper, glass of water, and just go through the steps, and it all works out very nicely, and you feel really good about it. So, nice work. See you in the next one. Okay, this is one of my favorites. We're going to show that sigma hat is a biased estimator, not an unbiased estimator, but sigma hat is a biased estimator of sigma. So what we're going to try to show here, we're going to show that the expected value of sigma hat is not equal to sigma. So, and we may even be able to show an inequality one way or the other. So, so great. So what we're going to do here is we're going to start with this. Start with the fact that the variance of sigma hat is greater than 0. So from sample to sample, we're not going to get the same sigma hat. We're not going to get the same estimate of the variance. So variance of sigma hat is greater than 0. And so from here, we can see that the variance of sigma hat equates to the expected value of sigma hat squared, right, minus the expected value of sigma hat whole thing squared is greater than 0 by substitution. Just variance of sigma hat, that's the variance of, say, that's sigma hat, that's the expected value of sigma hat squared minus the expected value of sigma hat squared. So we just, by substitution there, we've got that. So this would imply that the expected value of sigma hat squared is greater than this. If we take that to the other side, the expected value of sigma hat squared. Awesome. So that would imply that if I take the square root of the expected value of sigma hat squared, that will be greater than the square root of the expected value of sigma hat squared. Well, that side's easy. Let's start over there. The square root of the expected value of sigma hat squared is just expected value of sigma hat. And this side, we recall that this is the square root of the expected value of sigma hat squared. Sigma hat squared is an unbiased estimator for sigma squared. So if that's true, then the square root of sigma squared is sigma, which is greater than the expected value of sigma hat. And there we have shown that the expected value of sigma hat is not equal to sigma. In fact, it is strictly less than. The expected value of sigma hat is strictly less than the actual value of sigma, meaning that sigma hat is a biased estimator of sigma. Really cool stuff using some identities. Great job. See you in the next one.